Hi everyone, welcome to this week's session in which we will be looking at analysing repeated measures data using mixed models. So I'm going to start off by firstly introducing mixed models and various different considerations, including the advantages that they have over other techniques. But first of all, I just want to refresh your memory a little bit more generally on what repeated measures designs actually mean. So, broadly speaking, in the broadest terms, they are designs in which participants contribute more than one data point. So, for example, in an experimental design, participants take part in more than one condition. So, actually, repeated measures designs are relevant or incorporate quite a variety of different research methods and designs and approaches and are applicable to many different types of research question. So for an example, an experiment looking at differences before and after an intervention or treatment where a participant provides a before and after score. A repeated measures approach might also apply to a longitudinal survey, looking at differences between participant scores on a variable or variables at several different time points. It might also be relevant to an experiment looking at differences between scores on two different comparable outcome measures taken at the same time. So for example, if you're looking at measuring in-group bias, favoritism towards a group that we belong to compared to another group, then you might look at the difference between the rewards the participant allocates to in-group members versus out-group members. So you have a measure of rewards to in-group members and out-group members, and you compare those in a repeated measures analysis. So what I want to do is sort of highlight the value and the usefulness of a mixed models approach to analysing repeated measures data. So you will so far have thought of repeated measures data as something that you tackle using repeated measures analysis of variance. Now, mixed models are a really nice alternative to a repeated measures ANOVA approach. Mixed models are also sometimes referred to as hierarchical or multi-level models for reasons that we'll see in a bit. So why think about using a mixed model rather than a repeated measures ANOVA? Well, a mixed model has several advantages over repeated measures analysis of variance. One is that it doesn't have that assumption of sphericity. So if you recall from your repeated measures ANOVA coverage last year, sphericity refers to the assumption of equality of variances of the difference between pairs or combinations of conditions. Okay. So when that assumption is violated, when you have non-sphericity, you have to apply a correction term to the degrees of freedom, which then makes the test more conservative. Okay. In contrast, for a mixed model, sphericity is much less of an issue. Mixed models are also better able to handle missing values. So in a repeated measures design, in repeated measures ANOVA, if you have a missing value for a participant for one of the different measures that they provide, then they get deleted listwise, they get removed entirely. Okay, whereas mixed models has a more flexible approach to handling missing values. Another nice feature of, or potentially nice feature of a mixed model approach is that it can treat time as a continuous variable. What I mean by that is if you have, if time is a variable in your study, so you're maybe taking measures from participants at several different time points, you can actually include information about the length of time in between those time points. So let's say the time difference in time points is 2 weeks between the first and second time point, but then 6 months elapse between the second and third time points. That's a much bigger length of time. You can actually include that as a value. Okay. In contrast, repeated measures ANOVA will only really treat time as a categorical variable, time 1, time 2, time 3, rather than allowing you to quantify the amount of time that has elapsed. There are some other sort of similarities and differences, and rather than go into them in more detail, I provided a link to a nice summary of some of those similarities and differences between mixed models and repeated measures ANOVA. So, what is a mixed model? Well, it's actually a really, really useful approach to analysis that has applications that go way beyond the sorts of cases that I'll be covering in this week's lecture. So fundamentally, it's an analysis approach that allows us to take into account the fact that the data that we're interested in, the observations that participants provide, are often clustered within higher order groups. So for example, if we are interested in anything to do with, say, developmental psychology, and we are recruiting participants who are children in their school settings, we might want to take into account that at least some of the variance in whatever we're looking at is due to the fact that they are clustered within different classrooms within a school, or that they are clustered in different schools if you are testing kids from many different schools. Okay. Now, in terms of how that applies to the sorts of designs that we're going to be looking at here, the way of thinking about that principle that our data are often clustered, okay, is that in a repeated measures design, we can think of participants as providing a cluster or a group of observations. In other words, a participant doesn't just provide one observation, they provide two or more, a cluster of observations. Now, a mixed model takes this into account. Okay, so participant 1, participant 2, participant 3, that participant identifier gets entered as a cluster variable with what we call a random intercept. Now, a random intercept is just a way of building into the model the assumption that the mean value for each participant is simply drawn at random from a larger population of participants and potential mean values rather than having a fixed value. So that's all that means. And what that allows us to do is look at the effects of our independent variables while taking into account the fact that our observations by each participant may be non-independent, okay, because they're from the same participant. Okay. Now, just before we get going, a really important thing to highlight here is that is the practical difference that you will see in how the data are set up. Mixed models in jamovi need to be formatted in what's often referred to as long format, as opposed to the more traditional wide format, so-called wide format, that you would have data set up in for repeated measures ANOVA. Okay, so what do we mean by long and wide format? Well, here's an example of a traditional setup for wide format data, where each row in your data set represents all the observations from one participant. Okay, so here we have a repeated measures design where each participant provides scores on some variable at 3 different time points. Okay, so in each row we have those 3 observations from a given participant. Here's participant 1, who scores 20 at time 1, 15 at time 2, and 5 at time 3. Now, in contrast, long format data, okay, that reformats the data so that each row instead represents one observation from a given individual. And if a given individual provides more than one observation, then they are allocated to different rows. Okay, so look at the way the data is set up here for that same participant's data. Rather than all being in the same row, we have the first row providing their score from time 1, the second row providing their score from time 2, and the third row providing their score from time 3. Okay, and we also now have a variable that identifies which time point the value comes from. Okay, so it looks a little bit more like you would set it up in a between participants design. All right, with the exception now that because each participant provides more than one observation, each participant has more than one row. So that's what long format means. Now, just by way of reassurance, I want to say that for anything to do with mixed models and repeated measures data, all of the data files that you will need in this module for practicals or for the exam will already be in the correct format. Okay, so none of the assessment or practice in this module will require you to reshape or reformat data. Okay, but if you did need to convert data from wide to long format, for example, if you're going to apply this in a final year project, I've included a link to another guide on how to do this for different types of research design in Excel. Okay, so let's have a look, or start to look at mixed models in practice. Now, as I emphasized last time round in relation to between participants ANOVA, one of the things I want to do is get you to think about these different techniques or different analysis options in the context of a slightly more meaningful research question, okay? And look at how, as our research designs change, as we add complexity into it, we start to analyze or test research questions in more complex ways, the impact that that has on the analysis options that we have. Okay, so as I did last time, I'm going to start out with a research question. Think about how we can examine that in the simplest way in design terms, and then build some complexity on top of that to look at how it shapes our analysis options. So the research question we're looking at this time around is, does students' alcohol consumption change over the course of a term? So a very simple design might involve testing the prediction that alcohol consumption will be lower later in a term. There is lots of fun at the start of a term, but then as assessments kick in, maybe money runs out as well, alcohol consumption decreases over the course of that term. So what a researcher might do is design a simple study where participants self-report their alcohol consumption over the week at 2 different time points. Firstly, at week 2 of term, and secondly, at week 9 of term. Firstly, to avoid perhaps Freshers Week or Welcome Week at the start, and then to avoid assessment time or term time or people leaving early to go home towards the end of term. So they choose week 2 and week 9. 2 time points, one towards the start of term, one towards the end of term. And we can represent that prediction schematically. We have an outcome variable, alcohol consumption, measured in UK units, which is predicted to be higher at time 1 than it is at time 2. So our analysis options here might be, on the one hand, because we've only got two conditions, as it were, 2 levels, we could use a paired samples t-test or a one-way mixed model. Okay. So I'm going to show you how to set up a mixed model to test that in Jamovi. Okay, so here are our data. We have it in long format, so each participant has 2 rows because they provide 2 observations. Okay, this is the participant 1's observations at time 1 and at time 2. Okay, so let's set up a mixed model to test that prediction. And this is their score, by the way, in terms of units of alcohol consumed. So again, we're going to linear models, the Gamma LJ3 module. This time we're going to linear mixed model. Okay. And here's where we specify the model. Our dependent variable is our outcome, our score. Okay. Our factor is the variable that provides the repeated measures structuring of the data, variable or variables. In this case, that's time, where we had time 1 and time 2. So I'm entering time as the factor. Now, the last thing we need to do to make this a mixed model is under random effects, is to specify our cluster variable. So participant here, we have a variable that identifies the participant that the observations came from. Now, I emphasize that in repeated measures designs, a participant provides a cluster of observations. So the participant identifier becomes our cluster variable. Okay. Almost the last step then is under random effects. We want to say that participant as a variable has a random intercept, that idea that the mean value for each participant is just drawn from a wider population of varying mean values on participants. Okay, so we've got our output appearing. One last thing, a little bit like the between participants ANOVA, I'm going to ask for the estimated marginal means. So here we have our output, and there's quite a bit of output. So I'm just going to pop back to Jamovi and run through it. And specifically also in comparison to a paired samples, a repeated measures t-test, which I conducted separately on data in wide format. So here's the t-test output, and here's the mixed model output that we just saw. Okay, and this is the key table here, the fixed effect box, which is basically it gives you the information on the test of the overall effect of time. And again, a little bit like the point I made towards the start of the between participant ANOVA section, these are both just different versions of a general linear model approach to testing the prediction. They are functionally the same thing. Again, the F ratio here is simply the t statistic squared, and we have identical p-values. So again, the moral of the story is, for a design like this, if you run a mixed model or a t-test, there's no point in then also doing the other analysis because it will be redundant. These are just different versions of the general linear modeling approach to testing your prediction. Okay. So in a mixed model, it's more useful, a little bit like the ANOVA approach, when we have a slightly more complex or nuanced design. So let's take that same research question, okay, and extend the design a little bit. Okay, so the prediction now is that alcohol consumption will be lower later in a term compared to early and midway through a term. Okay, so what we're suggesting here is that the design has, rather than 2 levels, it has 3 levels. Okay, 3 time points. Firstly at week 3, then at week 6, and then at week 9 of term. So at 3 time points separated by equal-sized intervals. Again, schematically, what we might predict is our outcome variable, alcohol consumption, is highest at time 1, and then decreases at time 2, and then in turn again at time 3. Analysis options here, a one-way mixed model. So that again, a little bit like any one-way design in a general linear model, that provides us with an overall test of differences over time. Do the time points differ overall? And also allows us to drill down a bit further to conduct specific tests that compare individual time points or combinations of time points, and also specific trends across those time points. So to test trends, last time round for Between Participants ANOVA, I provided an overview of the different factors coding options that allow you to conduct different types of contrasts between levels of a predictor. Okay, so in much the same way, you can do that in a mixed model as well. What I'm going to focus on here is polynomial coding. Excuse me. Polynomial coding will give you the different shapes of trend line that could be fitted to your data. Okay, because we have 3 levels, we will get an estimate of a linear trend and a quadratic trend. A linear trend is assuming that the trend across the time points is a straight line of some shape or another, and a quadratic a quadratic trend suggests that the best fitting line has one bend in it. So perhaps the data start low and then increase and level off, or they start high and go low and then level off. Okay, so there's a bend in the trend line. If you have more than 3 levels, you have other types of trend line. So you have linear, quadratic. If you have 4 levels, you could also test a cubic trend line. If you had 5 levels, you could test a quartic trend line. Those respectively have 2 and then 3 bends in the trend line. Okay, but for our purposes, with 3 levels, we have a linear and a quadratic contrast. If instead we wanted to compare specifically the time 3 outcome with time 1 and time 2 combined, then we might select difference coding, which, as I said last time around in relation to between participants ANOVA, difference coding compares each condition or level with the average of all of the levels that precede it. So if you choose difference coding, you will get a contrast between time 3 versus time 1 and 2 combined, and between time 1 and 2 while ignoring time 3. Okay, and I'll show you those each in turn. So let's do a run through. Let's go to a different data set. Okay, so again we are looking at linear models, a linear mixed model. Score, their alcohol consumption score, is our dependent variable. Time, again, is our factor. We're going to enter participant identifier as a cluster variable, for which we are asking for, under random effects, a random intercept. Okay. And then also for the estimated marginal means. Now the key thing here as well is we're interested in the trend lines. Okay, so under factors coding, I'm going to change it first of all from the default simple coding to polynomial. Okay, so again here we have the fixed effects box, or the fixed effects table, which gives you the overall effect of each of your independent variables. In this case there's only one, time, so there's your F ratio, your numerator and denominator, or residual degrees of freedom, and the p-value, so highly significant effect. Okay. Under parameter estimates for fixed coefficients, we've got those two contrasts. Okay, a test of the linear trend and a test of the quadratic trend. Okay, those have an estimate, a t-statistic, and a p-value. Okay. If we skip on down, we have our marginal means as well. Okay, so just to dive into that a bit further, we can ask for descriptive statistics. This is that main, the effect of the overall, the table of the overall effect that I pointed out. A highly significant effect of time. That linear trend is highly significant. Okay. So it looks like the data fitted a straight line trend quite well, but the quadratic trend was not significant. So that suggests that whatever the trend is across those 3 time points, it didn't involve a curvy linear effect. Okay. If we had changed the coding option, factor coding option for time, to difference coding, these are instead the contrast that we would have got. We would have got the contrast between time 3 versus time 1 and 2 combined, and between time 2 and time 1. Okay, both those contrasts are highly significant. Okay. So again, often we are looking at phenomena that are not simply the product of one independent variable, or have more than one, or sorry, that only have one cause. Instead, the stuff that we're interested in is often caused by the interplay of many different variables. So when we're addressing research questions such as this, we might want to make our designs more complex by adding in additional independent variables. Okay. And more specifically, we might theorize that not only is our outcome variable affected by more than one independent variable, different independent variables affect the effect of other independent variables. Okay. In other words, we have, or might predict, interaction effects. That is, the effect of one independent variable is different at different levels of another independent variable. Now, when it comes to setting up analyses for any study that has repeated measures elements, it's really crucial to consider whether that second or third or whatever independent variable also has repeated measures. So in other words, all participants take part in all conditions or complete all measures. Or is our second or third independent variable actually between participants? So they take part in one of those conditions or levels only. If it's between participants, then we would refer to the study as having a mixed design. In other words, a design that combines both repeated measures and between participants independent variables. Now, I just want to emphasize, and this is quite understandably a potential point of confusion, a mixed model does not necessarily imply a mixed design. So a mixed design refers to the design of the study, okay? Whereas a mixed model refers to a form of analysis that can be fully repeated measures or actually fully between participants potentially as well, okay? So just be careful about confusing a mixed design, which is a design that includes repeated measures and between participants independent variables, and a mixed model, which is an approach to analysis. Okay. So let's start first of all with a design in which we have two independent variables, both of which are repeated measures. Okay. So I'm going to give you another research question here, a slight sort of change of track. A researcher is interested in whether alcohol consumption affects performance on hand-eye coordination tasks. Okay. They have a quite straightforward hypothesis. Consuming alcohol will reduce performance on hand-eye coordination tasks, but only for difficult tasks and not for easy tasks. The idea being that maybe alcohol consumption maybe reduces or relaxes the body, etc. So it doesn't inhibit the performance of easy tasks, but actually for difficult hand-eye coordination tasks, then consuming alcohol compared to being sober will have more of a detrimental effect. Okay, so given that hypothesis, we might set up a study that has two independent variables. Let's say alcohol consumption, which they vary as being a control condition, sober condition, and an alcohol, so tipsy condition, okay? And repeated measures, so participants do both of these. And the second independent variable is task difficulty, the difficulty of the task that they are asked to perform. That also has two levels, easy tasks and difficult tasks. Again, repeated measures, so each participant completes both easy and difficult tasks. And the hypothesis here is that the effect of the first independent variable, alcohol consumption, will depend on or be different as a function of the second independent variable, an interaction effect. Okay. So procedurally, because it's a repeated measures design, we just have to be careful with this to make sure that, for example, completing the control condition first doesn't have different effects compared to completing the alcohol condition first. Okay. So each participant maybe attempts the hard and the easy tasks without consuming alcohol and then does them again after consuming alcohol, or vice versa. They start with the alcohol consumption tasks, then sober up, and then do the control tasks. Okay, so it's counterbalanced. In terms of a schematic, we could represent it as follows. So this is our outcome variable, performance on hand-eye coordination tasks, notionally scored out of 20. Okay. Excuse me. So here we have the effect of alcohol, the contrast between the control and the alcohol conditions, broken down by task difficulty. This is the effect of alcohol in the easy task conditions, so no difference. And this is the effect of alcohol in the hard task conditions. So we can see we're expecting a drop-off in performance in the alcohol condition. So our analysis options here, a two-way mixed model, again two-way, two independent variables, which will test, again, a two-way design gives us three effects. The two main effects of each of the independent variables, and the third effect, the interaction between the two independent variables, which is the test of the extent to which the effect of alcohol varies in turn as a function of task difficulty. So let's see that in action. So a new data set here. We're again looking for linear models and linear mixed model. again, score is our dependent variable. This time we have two factors, two categorical independent variables. We have alcohol and we also have task difficulty. All right. Again, we're entering participant as our cluster variable. That's the participant identifier. If I just go back to the data, I'll show you how it's set up. So we have the participant identifier. This is participant 1, providing 4 scores. Okay, this is their score under the influence of alcohol for easy tasks, under the influence of alcohol for hard tasks, sober for easy tasks, and sober for hard tasks. Okay, so that's the way the data are set up. So back to the model. We want to specify again that the participant identifier has a random intercept. Okay. And we're also asking for the estimated marginal means for alcohol, task, and the breakdown of alcohol by task. Okay. And there's the model, our table of overall effects, the two main effects of alcohol and task, and the interaction between them. Okay. As we move further down, that's the breakdown of the means. So it's back to jamovi. Here's that main table with the two main effects and the interaction. So we have the main effects of alcohol and task difficulty, both of which are significant, and we have the interaction between them, which is also significant. So that suggests that not only does alcohol have an overall effect, that effect in turn differs as a function of task difficulty. Okay. So that significant interaction is, at one level, consistent with that hypothesis that there would be an interaction between alcohol and task difficulty. But again, that prediction was a little bit more specific. It was more precisely that alcohol would affect performance more so or only for difficult tasks, not for easy tasks. Now, the interaction in itself doesn't tell us that that was the pattern that was observed. Instead, what we need to do is delve down a little bit further, just as we did for interactions in between participants designs, delve down a little bit further to look at the effect of alcohol broken down by each level of task difficulty. In other words, we need to conduct simple main effects analysis to decompose that interaction, to test that effect of alcohol at each separate level of task difficulty. Okay, and that's where we will pick up in part 2 of this week's session. Join me then.